Boeing, Canada, DeHavilland Division in the crazy 80s. What could go wrong? Well, it's time to travel back and clock in using the old punch card to your department.
DeHavilland Aircraft Canada Engineering. Engineering in the 80s, it was a different world. As most people know, it was the DeHavilland Beaver and the DeHavilland Otter that really put the company on the map. They opened up the north for Canada, bringing supplies into lumber camps and mining operations. Without them, Canada wouldn't be the Canada that we know today and love so much. My involvement with these aircraft as an engineer was primarily in testing the turbine powered variants in order to validate DPS run charts and data that was used for specifically engine tests. This is a picture of the Otter, owned by Bearskin Airlines and flown by Harvey Friesen
and Carl Friesen, two friends of mine. Carl is no relation to Harvey, they just share the same last name. Harvey and I used to fly together
with Northwestern Ontario Air Search and Rescue. Getting back to maintenance, we did a lot of upgrades on the old Turbo Beaver with the Dash 20 engine, and also the Twin Otter with the Dash 20 engines, the 100 series. We did a lot of custom build specs in order to make that engine more reliable. Here you see a Viking Air conversion Turbo Otter with a PT6A 135 engine. That's a 750 horsepower engine, flat rated to 600 horsepower in the Otter. They also used the PT6A 34 engine, distinguished by a smaller propeller and a smaller reduction gearbox. Both engines are flat rated to 600 horsepower installed. On the heels of the Otter came the Twin Otter, the first turbine engine aircraft produced by de Havilland Canada for commuter airline service. It was a versatile 19-passenger, small airline type aircraft that took de Havilland into a completely new direction. Here I am, island hopping in Royal Tongan Airlines Twin Otter aircraft back in the day. We helped the Tongans implement and operate their new fleet of Twin Otter aircraft. I taught them how to maintain and operate their engines. Tongan Airlines used the PT6A27 engines upgraded to Dash 28 specs. That meant that they flew the engines or operated the engines to a tighter T5 ITT limit of 1680 degrees Rankine on the test cell, as opposed to 1700 degrees Rankine for the Dash 27 engines. By use of coatings in the hot sections, they were able to achieve the same power ratings at cooler temperatures. This really helped them with their hot, humid temperatures in the down in the tropics in the South Pacific. This is a 100 series Twin Otter with the PT6A-20 engines that I mentioned before. These engines had an old style hot section assembly that was sealed up with abradable cord seals, which was really a problem that we worked on in order to make the seals more reliable by using metal jacket cord seals that they used in Rolls-Royce type engines. That helped the longevity and reliability of the hot sections. In the 70s, they introduced the Dash 7 aircraft. This was a STOL aircraft of 50 passengers and 4 turbine engines. Pratt & Whitney PT6 A50 turboprops. My first job at de Havilland Aircraft Engineering was to redesign the engine installation for the Dash 7 for the new Dash 7 200 series. It was a stretch Dash 7 aircraft that would use the new prototype PT6A 56 engines, which basically combined the A50 gearbox of the A50 engine of the previous Dash 7 with the new 65 four-stage axial compressor of the PT6A65 engine, whereas the original PT6A50 engine had only 3 axial stages in the compressor. Here's a nice picture of the Dash 7 flying with a Dash 8 airplane in Toronto over Billy Bishop Toronto Island Airport. There's the CN Tower in the background and a younger Toronto. The extra horsepower would be required to stretch the aircraft from 50 to 75 passenger seats. This turned out to be a complicated project because if you look at the picture, you'll notice there's a rear shelf and then a cell that supports a rear engine mount, which is on the bottom of the accessory gear case attached to the back of the axial compressor. And then there's a horse collar up front that establishes the front mounting plane ahead of the compressor. So with a longer four-stage axial compressor, space became a problem. There wasn't enough room to push the engine back on that rear shelf without it colliding with the structure just ahead of the wing spar, the forward wing spar. So we ended up doing a lot of work in order to fit the engine in properly. And still we had to move the engine slightly forward, which changed the center of gravity of the engine in the wing, which was a big program. In the end, they decided not to go ahead with the airplane, and we rolled up our drawings and submitted them to archives, sadly. In hindsight, from an engine perspective, that was probably okay in the sense that the PT6A65 turned out to be a real dud for Pratt & Whitney, with hundreds of campaigns and service bulletins issued on that engine. It really wasn't until they came out with a 67 that they had a good engine. While the original A50 as used in the Dash 7 was a very good engine. The first Dash 7 flew in 1975 on March the 27th. And here we are with our lovely wives during the rollout of the 300 series Dash 8, standing next to the old Dash 7 parked outside of Bay 5. And this reminds me of a funny story, a true story, where, we got paid in the old days in cash. And on Friday, on payday, you'd get a little brown envelope with a stamp on it from the payroll department with all the deductions handwritten on there. So, of course, a lot of the guys Friday night would take off and visit the local bars and pubs, and the wives figured that out pretty quick. So leaving the plant, the wives would be waiting at the main gates for their man to come through with their pay in their pocket to intercept them. And I gotta say, I never seen so many pretty girls and women waiting for the boys to leave the plant. I used to think, oh, wow, those married guys are the luckiest guys in the world. And then I got married. And now I'm the luckiest guy in the world. Still am. Following the Dash 7, the timeline takes us to the Dash 8. What a marvelous aircraft. It was a fleet leader. People loved it. It was a market leader. Basically stole the market. Basically, it created a market that never existed before. With the advent of the Dash 7, DeHavilland Aircraft started to realize that many of the operators that purchased the Dash 7 really weren't using it as a STOL type airplane that the Dash 7 was designed to do. And they didn't really need to pay the higher penalty of more drag associated to a high lift wing. They were mostly using the Dash 7 as a commuter type aircraft. And so they didn't need to have the STOL capability and 4 engines of the Dash 7. Of course, engine development was developing leaps and bounds at the time. DeHavilland Aircraft Canada, in conjunction with Pratt & Whitney Canada, was developing the new PW100 series engine, which would be the future for the Dash 8, with a PW120 variant that was able to produce 2,000 shaft horsepower. So they no longer needed to use 4 engines and could get away with just 2, minimizing complexity and drag and greatly increasing aircraft efficiency. With a new streamlined wing, fuel burn was much less than with the Dash 7 aircraft, and it quickly became the new greatest thing. Everybody wanted one, and therein lied the problem: production. De Havilland Aircraft was never used to having the order books full to produce so many aircraft so quickly. It was overwhelming. The factory was stressed. De Havilland Downsview in Toronto was a different kind of aircraft factory, in the sense that back in those years, every single part, other than, standard hardware, nuts and bolts, and off the shelf items like instruments and engines, etc. But basically, every part, every bracket, every wing, the wing section, the fuselage, the parts, the rate items that went into the plane, everything was jigged and fixtured and manufactured on site, including composites, wiring, all small items, small brackets. Everything was made under one roof in that factory. It employed about 5,500 people at that time in Toronto. And it was, in a way, unheard of in the aircraft industry. As the aircraft industry progressed, there was a new terminology called the rate item build, which was basically building components more efficiently at specific factories, that would all come together at final assembly, and the aircraft company would do the final assembly and put it all together. This wasn't the case at de Havilland Aircraft in those years in Toronto. The rate item builds were basically designed to fit into a standard shipping container. This way, parts could be made by low-cost labor centers in different countries around the world and shipped to the final assembly facility. Unlike de Havilland, that made all the components basically from comparatively expensive Canadian labor. Here's my friend Robin Law that worked with me in power plant engineering. He was the engineer that did a lot of the flight testing in Arizona for hot weather. Test on the Dash 8 200 series to verify the PW123 engines for the upcoming 300 series. Another problem we had back in those years was that the drawing system was fairly antiquated, and computers needed to be implemented soon. I worked propulsion design on the oil cooler installation, the bypass doors, inertial separators, and also the APU installation. A big problem they were having was the fact that there were so many different customers that were opting for Dash 8 airplanes that every customer, every airline wanted it a different flavor and slightly configured differently in terms of the interior and where the lavatory was and where the coffee station was. And everybody wanted a different thing. And the factory was very stressed out in terms of manufacturing and methods on how to control so many what they called customer requests, changes to the design, that was all of a sudden warranted by so many different options and so many different customers. The other problem is the workforce was kind of used to building one thing. So you had the problem where guys on the line didn't understand the drawings and the changes and the amendments that were required. So when they were building airplanes, sometimes they were just going to the airplane that was already ahead and finished and sticking their head in the panel or in the interior and looking to see how it was made and just making it the same on the aircraft that they were now building. So that became a real problem in terms of reworks that needed to be done when those problems were spotted. You know that the aircraft wasn't built properly or correctly. So, wow, there was lots of rework, lots of overtime, lots of overruns in production, and lots of cost associated to it. That set the stage for DeHavilland Aircraft to look south, to look at what Boeing was doing in terms of manufacturing to speed up production, which led to talks and the eventual takeover of DeHavilland Aircraft, the government corporation, taken over by Boeing Aircraft Company for a grand total of $55 million and a defunct factory that needed an environmental control system for another $50 million, which included other factory upgrades as part of Manufacturing Action Plan 87. I've included a lot of the slides on this presentation talking about the Boeing Canada de Havilland Division merger with a lot of extra detail if you're interested. Well, it's hard to imagine it all started with this simple DHC-1 de Havilland Chipmunk airplane. The years got more and more complicated, and by 1987, Boeing had taken over the reins of the government company known as the de Havilland Aircraft of Canada. It was now Boeing Canada de Havilland Division. Big changes were on the horizon. Down in the plant, they were fighting the production wars, and Boeing had established a manufacturing change board to better integrate customer changes, which was badly required. And up in the engineering office where I worked, they were making a lot of changes too. They were moving away from the old drafting tables and getting into the CAD CAM systems that they used at Boeing. I think the first one that we got was called the Cadra 1 system. That was a big change and culture shock for a lot of the old guys that had been with the paperwork system since the Avro Aero. A lot of the old guys were actually from that program when that went out of business in Malton in 1959. A lot of the engineers and designers came over to Canada, which lent such great expertise to advance the company fairly rapidly from that point on, from Bush aircraft to NASA jet engine powered aircraft in what was a very short period of time. I'd be remiss if I didn't say now that I apprenticed under Clay Dite, and Clay was an excellent designer that had been with the Avro Aero project and had actually smuggled drawings out at the end when the Canadian Army was shutting the plant down. He was the designer of the exhaust ducts and the intake system on the Avro Aero, and was I'm proud to say that I learned a lot about design from Clay. And I can give you some more insights of the men that were there at the Havilland Design back in those years. And for example, Fred Black, he was our Air Systems design chief. And Fred had flown with the Canadian Air Force. He was a vampire pilot. Terry Irwin was the manager of propulsion design and engineering. He was the DAR for all power plant systems, the design approval representative. At the end of the day, Terry's signature had to be on the drawing if the airplane was going to fly. Ken Kingswood was the vice president of engineering. He was a tough man, but a fair man, and he got the job done. He was very well respected by all the de Havilland engineers and technologists and design staff. Other great guys in propulsion engineering was John Black, Larry Mamatosis, John Ford, John Farmer, Carwal Mack, and Derek Hiscock. All very talented people. Dave Thomas and Steve Rose were the propulsion design group leaders. They were great guys to work with, and they knew how to do amazing things with pencils and paper. One other big change the Boeing people did in the design office was to tear down the wall between the aero engineering department and the manufacturing engineers. It was just too much a case where, basically engineering ruled the company in the early days of the DeHavilland aircraft, and in a sense, kind of just threw the drawings over the wall at the manufacturing guys to get done. And in the fast paced world of several customer changes and different options hitting the design in a quick succession, which required manufacturing input earlier on in the process. This is the big change that they made to get the aero engineers to start working with the manufacturing engineers hand in hand to make the changes and to get the right things ordered earlier on in the process to facilitate just in time manufacturing of the aircraft on the line. As well, Boeing was trying to streamline the entire company, including engineering. And there were some great engineers and efficiency guys that they sent from Seattle that I had a lot of respect for. Guys like Ralph Dines, Tony Zinicola, Lou Espinoza. These guys were unbelievable. They're very nice people to work for and really made the difference. They used a company called Vertical Systems Integration in order to plot all the engineering flows, material flows, manufacturing flows in the company. At one point, they even used the entire hangar wall to map out all the bits and paper that was required in order to make an airplane from start to finish and then adapt that into a digital world. As well, they were really big into continuous quality improvement and had some experts like Marty Dreves. I mentioned Ralph Dines before, Mike Walton, Bob Cracknell, all these guys basically implementing Japanese continuous quality management principles in Canada, following the Demings and Conway program. There was so many new initiatives being implemented by Boeing all at one time. It was unbelievable. It was hard not to be optimistic about the future. Down in the shop, it was people like Floyd Ertel that really went the extra mile. And we had started the design work on the Dash 8 300 series airplane. And this was a stretch version of the Dash 8 100 series. It used two 6-foot plugs before and aft to the wing spar in order to increase the volume of the fuselage for 50 passengers up from 35. Unfortunately, disaster strikes. The CAW contract expired in 1987, and the CAW union instructs the workers to go on strike, thinking that the new companies got all kinds of money to throw down, unhappy with the wages, and looking for increased job security due to outsourcing being talked about. During the strike, anybody in the engineering department, which is management, continued to work and develop the new design for the 300 Series Dash 8. And those of us that had manufacturing or aircraft experience as a mechanic were to return to the shop floor in order to build 6 aircraft and deliver them on schedule or as close to schedule as possible so that Boeing wouldn't have to take a hit, financial penalty for being late on those aircraft. I think it was during the long strike that Boeing really had to have a hard look at how much money they were spending in Canada and what they were going to get out of it, if it even made sense. Well, there was some happy days. Here's a picture of my brother, Glenn Bloomberg. He was the production supervisor of the very first Dash 8 300 series that was built. Here he is being hoisted up by his crew after completing the first Dash 8 300. Glenn had a lot of manufacturing engineering experience, a graduate of Ryerson University. He also had a lot of mechanical knowledge, a graduate of the Centennial College Aerospace program. So they selected Glenn to build that first airplane. We're very proud that he was able to do it on time and ready for rollout. Later on, he went to Boeing in Seattle. He was given a job personally by Ron Woodward, the president of Boeing. Glenn was instrumental in engineering the 777 for Boeing. Production had been very slow, with the estimated man hours to complete a Dash 8 aircraft in around 72 to 75,000 hours to completely deliver the airplane, and yet they were in around 125,000, 150,000 man hours to build a single unit. And this really cut into the profitability of making airplanes in Canada. And that number wasn't coming down due to the strike. They settled the strike by giving everybody a $3,000 ratification bonus to get back to work. But I think by then they had really seen the red ink running. And the final nail in the coffin was the Mulrooney scandal that, you may have heard that Mulrooney at one point was taking a payoff from Airbus, and Air Canada, at the time being a government company, purchased Airbus aircraft instead of Boeing. And I think Boeing really needed those contracts to make their company viable in Canada, to support the losses that they were getting at DeHavilland. And so without the Boeing Air Canada contracts, they of course buying Airbus A320s. Boeing was at a loss. And I think, in my own opinion, that was the reason why they, soldiered on for a couple more years. But by 1989, mass layoffs had started, with the company shutdown on the horizon into the early 90s. And certainly by 1989, other competitors had moved into the space with their EMB 110 and ATR 42 aircraft. Sadly, some of the challenges we had in propulsion design when doing the 300 series Dash 8 was hotter oil temperatures, and because of the larger engine and more powerful PW 123 engines, we had some challenges to overcome with the oil cooler design. If you looked at the bottom of the nacelle, you could see that the front nacelle clamshell opens down and it's hinged at the back. And then behind that clamshell, there's about 10 inches of structure. And then you'd see the bypass doors for the oil cooler. And the main problem was the oil cooler lies flat in that 10-inch space. And there lied the problem with poor flow going through the oil cooler, with the larger engines producing more temperature. On one engine hot climbs, we were right at the maximum allowable oil temperatures. With the PW 123 engines producing 2,300 horsepower in the 200 series Dash 8, which was basically a test vehicle for the 300 series. Of course, later on, they marketed that as a Hot Rod 100, and some aircraft operators preferred the 200 with a higher horsepower. However, internally, those engines did run hotter in the gas generator, the combustor, to make the extra power. And so oil temperatures, of course, were the issue. If you're doing a walk around on a Dash 8 100 series with the older PW120 engine installed, as you look into the intake from the front of the engine, looking rearward, you can see a primary intake cone, which basically supplies air to the compressor intake on the engine. To the rear of the first intake cone, you'll see a smaller cone that is designed to facilitate the installation of an inertial separator bypass door. And you'll see at the back of that cone the face of the bypass door, as the bypass door is selected closed, as it would be on the ground during a walk around. Intake airflow at the back of the primary cone before it enters the bypass door cone, the second cone, spills over into the oil cooler pathway and passes through the oil cooler element and then out the bottom oil cooler bypass doors, which are flat mounted at the bottom of the nacelle. When you're doing a walk around on a 200 or 300 series and you look through the intake, things look a little bit different in the sense that at the back of the secondary intake cone, you can see the bypass door. However, the forward face of the bypass door has been opened up, and that allows more air to spill down into the oil cooler pathway and help with the airflow through the oil cooler. This modification helped get more air through the oil cooler, as mentioned, and didn't change the operation of the inertial separator or bypass door. It still functioned the same way, only it was opened up at the front of the door of the bypass door. At the back of the secondary intake cone, you can see it when you look through the air intake. As Robin will tell you, that was enough to certify the aircraft during hot weather testing that they did in Arizona. So it worked and served to lower the oil temperatures across the operating range of the airplane. Something that I'm proud to say that I had designed the secondary intake cone inertial separator way back in 1987, and it's still used today. As Robin mentioned, and the other guys could probably tell you that we're down there testing, not to come home unless you got it done, that we had a backup plan. And one other thing that I designed was a forward-facing fiberglass or Kevlar air scoop that could quickly be added to the bottom of the nacelle, just aft of the bottom clamshell door and ahead of the landing gear doors, immediately underneath the oil cooler exit doors. And this backward facing scoop would accelerate the airflow, the laminar flow at the bottom of the nacelle, and create a low pressure drop just ahead of the exit of the oil cooler airflow to help accelerate the flow through the cooler to lower the oil temperatures. I designed it. It was all ready to go. They took it with them. The experimental prototype shop built it. And as I said, they took it with them. But it turned out they never had to install it. They didn't have to use it. So luckily, it didn't get used. And that was nice because otherwise the Dash 8 would have to have this ugly scoop, backward facing scoop on the bottom of the nacelle and spoil the nice racy looking lines that the Dash 8 was famous for having. I also designed the APU installation, the auxiliary power unit. It was basically an Initech design that we had used in the 100 series Dash 8 that I cleaned up for the 300. It wasn't great. Most of the work I had done was to kind of rearrange components and position it a little bit better in order to make it, ergonomic for the mechanics to work on it. It was back in behind the pressure bulkhead in what they called the hell hole. It was only a ground operable APU. However, it was very difficult to reach, so I tried to reposition it in order so that you could reach around behind it and maintain it properly. There was no budget to do much else in terms of the APU project. Later on with the Dash 8 400, when we did the PDR preliminary design review on that aircraft, we put the APU in the tail cone of the airplane, where basically a fiberglass tail cone could come off and expose the APU entirely, making a lot easier location to work on and also air operable. Well, I think that just about covers it from a propulsion engineering design standpoint. Uh, Engineering wise, there was a lot of other challenges, probably more so than in the propulsion group. One of them with the fact that by adding the 6-foot plug at the back of the wing to increase the length of the fuselage, push the empennage tail section too far back, and on rotation to clear an obstacle type takeoff or maybe a bad crosswind heavy landing, there was a tendency for the tail to touch the runway or possibly touch the runway because the angle was too far back. So they actually had to redesign the landing gear, I believe, so that when the gear swings down, the wheels were actually, I think it was 10 or 11 inches, maybe slightly more, towards the rear in order to allow for enough clearance. I believe Jimmy Matthews and Bruce Van Deuce were the designers on that one. I think some of the older landing gear designs were designed by Joe Giles as well. Joe was later on a weight and balance engineer on the Dash 8 300 series, and he was a excellent engineer and resource for us younger guys um, to learn from. He also really understood stress and loads that really helped us in the design of components. Joe had designed the landing gear on the lunar rover before he came over to DeHavilland way back in the early 70s, I think it was. And he was also my neighbor when I was a kid. Keep in mind, this was back in the day before computers and finite element analysis programs. It was a day when engineers used slide rules and relied on experience. And experience meant a lot in those years. What worked before was reapplied in many cases. Okay, a couple final pictures. Here's Floyd Ertel handing out an award back in the day. And then, of course, by the late 80s, we started working on the design of the new Dash 8 400 series and also the Q ships, which were the quiet interior aircraft. Well, if you're still with me, thanks for listening.